Nice. Thanks so much for coming, everyone. I'm going to be talking to you about some field work that I did in September last year, where I had the misfortune of being sent to northern Spain to hang out in the sunshine and hit rocks with hammers. If you'd like to tweet along, that'd be great. My Twitter handle was funnier when Donald Trump was more of a joke. So what are we going to do today? Firstly, we're going to have a little talk about why do we study repaired injuries? What's the point? What are you trying to do? I'm going to look into some of the history of the research that's been done. Then we're going to go and look at the Iberian chains, where we have 3 different sites, so we can look at things both different geographically and at different times. And then finally, we're going to look at a Bayesian inference, little bit of statistical play to try and deal with small sample sizes, because these injuries tend to be quite rare. We're going to run through 2 other sites I've been working on at Ruin Wash and Manuel's River. Then we're going to kind of sum it all up. So why are we looking at repaired injuries? So the big idea is that we want to understand ecology. We want to understand how dangerous Cambrian seas were and the effect of predation on trilobite evolution. And there's a bunch of different ways we can do that. We can use functional morphology. We saw earlier with Dave's talk about the sea scorpions. We can look in the guts and the poop to see what's eating what and how. And lastly, we can look at the skeletons of prey themselves. So we can look at both repaired injuries, like we have on the right-hand side there, and also unrepaired injuries. So the main reason to look at repaired injuries is we know that it happened during the animal's life, whereas unrepaired injuries can be a little bit more problematic. So if you think you've got a nice smashed piece of shell in front of you, how did it get smashed? Was it a predator, was it a scavenger, or maybe it happened due to abiotic processes? So to test this, we used a semi-landmarking approach. So we've had a lot of talk about morphometrics already, but just a quick reminder, we just used a semi-landmarking to describe the shape of the break. So you look at the one at the top there, we've got 2 big V's. We can kind of convince ourselves that maybe that's due to the action of an animal with a big crushy claw. The one at the bottom with its kind of more gentle curve, we're not so sure that's got a biotic origin. So we collect all of those semi-landmarks together and we plot them out in space, and we see there's no real good partition there. There's no real obvious way that we can use the shape of these unrepaired injuries to understand to understand that it was in fact of a biotic origin. And we can see that all these breaks from all these different formations, they all plot all over each other. There's no big story there that we yet have the skills to take out. So what might be causing these repaired injuries? We're not out of the woods yet, so repaired injuries know they happen during the animal's life, but that's actually, trilobites have a number of ways they can injure themselves. So the one there on the left, the harpies there, is torn the genal spine on the left-hand side there. And this is thought to be due to problems during molting. So when these guys grow, they'd attach their exoskeletons, and then the soft trilobite will slide out and then harden as it wants to increase its size. And the idea is that during that process, sometimes they can injure themselves. They can also look a bit weird with genetic malformations. So this poor guy's got a genetic malformation. He's got a nice lump on the outside of his skeleton. And finally, they can have these big bites taken out of them. So these bites have been known about for a very long time. And they've been found on trilobites from all over the world, of all ages, all different places. Babcock in 1993 kind of lumped all the literature data together and found that for Cambrian trilobites, these bites tend to be located on the rear and at the right-hand side, whereas for non-Cambrian, so all the ones from later on, that didn't hold. So what no one had done before was gone to one place and said, how many bites are here, how common are they, how likely is a trilobite to get bitten? So that's kind of what we were aiming to do in Spain. We're looking to collect frequency data on repaired injuries. We were going to test the literature to see if at this one place we have bites at the rear and the right-hand side. So this will help us understand the reasons. So Babcock put forward 2 hypotheses. One, that it was because predators themselves were right-handed. They've got a big right hand and a small left hand. And the other one could be that trilobites in the Cambrian are kind of like Derek Zoolander. They can't turn left. They always turn the same way, and that's why they always got in the same place. We also want to understand how important predation is in causing these injuries compared to the other 2 potential things, and then we also want to see the variation. So are all trilobites injured the same amount? Does it change depending on environment, taxa, all these things that could be playing an effect? So where did we go? Well, we went to Spain, to the Iberian chains. We went to 3 different sites. So 2 of them, Mesones and Purojosa, are both from the Drummian, so they're younger than the other site, Minastierga, which is from the older stage 4 in the Huemera formation. Mesones and Minastierga are very close together, whereas Purojosa is a few kilometers away. So we've got a bit of geographic distance, 2 sites of the same age, and all of these things are in the same environment. We used the finest and highest tech tools we could find, so we've got some nice crowbars there in the top left, and then nice big hammers. And Fernando and Jesus are local amateurs who helped a lot. They know this rocks extremely well. They're very good at finding trilobites. And they're also very good at plying you with Spanish ham and field wine to keep your spirits up towards the end of the day. And Samuel from the Spanish Geological Survey, he was an incredible help and a great collaborator on this project. So what we're studying some nice looking trilobites. So from the Minas Tirga, the older site, looking at red lichids, which currently are being described. And from the two younger sites, we're looking at the same species there, Echoparadoxides pradoanus. And we saw some really cool things. So this is probably one of my favorite outputs of this. We see trilobites in various stages of repair. So the one up there, we can see it just had a little nibble taken out of it, just where the arrow's pointing. They then start to heal by the spines round off in the next molt. In the molt after that, we see a little tip of the spine starting to process out. And then finally we end with some nice short spines that look pretty normal. The stage after this, we're just seeing big spines that look the same, and all evidence for the injury will have gone. So this is the kind of injuries we're looking at. So what can we say about the relative importance of the different types? So if you consider a molting injury when all your spines look the same, the chance of accidentally injuring anyone should be the same, so you expect it to be kind of randomly distributed, randomly arranged injuries, and similar for genetic malformations. However, if predatory origin, you're more likely to injure two adjacent spines. And we can see from that very low p-value that it suggests that these injuries are located adjacent to each other more often, and so that these injuries are likely of a predatory origin. How about asymmetry? So there was no support for asymmetry injury location, and from our limited samples, there is weak support for the rear three segments of the trilobite being injured more often than we'd expect. But more exciting to me was actually the locality data. So all our injuries were from the same place. The other two sites had no injuries at all. So what was causing this? And how can we dig down and see that this is potentially a real thing? So to do this, we worked on a new kind of use of Bayesian inference to try and compare these different sample sizes and get an idea of, if I only pick out 45 fossils and they all don't have injuries, well, maybe there are injuries there, they're just quite rare. How rare are they? And that's what we're trying to do. And also, we don't just want to get a p-value and say they're different. We want to see how different, what are we expecting? So how does it work briefly? Well, we start with a very uninformative prior, this beautiful straight line. And what it's doing there is just saying, I don't know how many injuries are in this site, which seemed fair because I had no idea. And then what we do is we just chuck in our data, so if we know the number of specimens and the number of injuries, we get these beautiful plots, and we can take any quartile you want. So you can say, I want to look at the 95th percentile value and look at the mean value, and that gives us an idea of the variation we expect from having these sample sizes and the probabilities of finding different things. So we can see here that at Porohosa, the curve is shifted far away from the other two, so we're seeing a distinct change here. We're seeing a different thing and a higher amount of predation. Why might this be different? Well, you could make a list as long as your arm, but these three are the things we're going to try and test to see if they might be making a difference. I'm going to do that by looking, firstly, at some museum specimens I've been collecting. So the error bars we're seeing are the 5th and 95th percentile of that curve we had before from the Bayesian inference. And we can see there's no real time correlation here. There's a few sites up the top which seem to have far more common injuries than everywhere else, but there's no real time thing. And we're going to look at two sites quickly just to try and understand a bit more. So at Ruin Wash, which is in the stage 4, so same age as the Huemeda Minas Tirga place we were looking at before, which had no injuries, we do have presence of injuries. We've also got 4 species of Olenellus over there on the right-hand side, which are more commonly injured than the not Olenellus species from the same place. This is showing us that even at the same place with all the other variables controlled, different taxa are injured to a different amount. I also want to talk about Manuel's River, which is in Newfoundland, because it brought me worldwide fame as being the Field Museum Fossil of the Week. And also I got some great ideas about what might be causing the damage. Someone suggesting that a cheeky human bite may be on the collectors, I'm not sure. And this reminded me of something I read on the Facebook literature, which, I mean, if you can draw hands like that, I think I've got to trust everything you say. But more seriously, it's because we've got these really cool subspecies here. So in the original work, you look on the left-hand side, you see that these different subspecies are found at different layers in the rock. And the idea is that the trapeza pig and the intermedius are from a more restricted environment than the Davidus davidus. So we find Paradoxides davidus in Wales and in the UK, but this is from the other side of the Atlantic, but we're looking at Avalonian trilobites. What we also see is that all the injuries on this type of trilobite are on the trapezopig and the intermedius, so they're from this restricted environment, whereas when we go out to the more open environment, we don't get nearly as many injuries, which is super cool and super interesting, and this is something I want to narrow down and learn more about. Whether it's the morphology of the trilobite that makes a difference, if you just look at the shape of their pygidiums, that's how you tell them apart. So the fact you've got this tiny pygidium changing shape is almost certainly not affecting the amount you get bitten. But we can see that the trapezopig gets bitten far more often than the Davidus, even with our small sample size, could have been bitten. So just to sum up quickly, we've seen in Spain, we've got 3 sites, where at one site we have a higher chance of being injured than at the other 2. And although this might have something to do with time, there's no evidence for that yet, that there's any temporal change. So it could be to do with the different taxa in the lower and middle Cambrian sites. But also, these slight changes in restriction environment can have a huge effect on the repair frequency that we find on these animals. So I'd just like to thank you guys all for listening and thank all these people for helping me along the way. And if you have any questions, I'd be delighted. Thank you.